Good afternoon, my dear grade 8 learners. Once again, this is our science time and I am Mrs. Dolores Fontanilla, your science teacher. This afternoon, we're going to take up now our quarter 1, week 4, which is about sound. Keep listening.
We are experiencing a rainy season now, where lightning and thunder are part of it. Do you notice that several seconds pass between the time you see lightning and hear thunder? How come you see lightning first, when actually lightning and thunder occur at the same time? What happens during this time lapse? This phenomenon is explained by variations in the speed of sound. Sound produced through vibrations. Sound is a mechanical wave that needs medium to propagate. They propagated through solids and liquids, and generally propagates and travels through air. This is the reason why you can hear a conversation on the other side of a room, even if there is a solid barrier in between. Waves are characterized as longitudinal waves. And what is longitudinal wave? Longitudinal waves are waves in which the vibrations of the medium is parallel to the direction of the medium, that is in the same direction of the wave propagation. The waves move back and forth or to and fro. This wave is characterized by a compression and rarefaction waves. As you can see, the wavelengths are of different sizes. There are portions that it is compactly arranged, and there are parts where the wavelengths are far from each other. So rarefaction, this is a segment of one cycle of longitudinal wave during a travel or in motion. That is the part when there is less pressure. So it is the wavelengths are far from each other. And compression, these are waves which are pressed together. Compression, from the word compress, they are compactly arranged. The speed of sound waves does not depend on the source, but on the medium through which they move. In solid, they are more dense. The molecules are closer together, which allow them to collide quickly with each other as sound moves through them. And in solid, sound travels faster compared to liquid, which sound travels slower than in solid. And of course, in gas, the sound travels the slowest. Several factors affect the speed of sound as it travels through a medium. And these factors are the density, elasticity, and temperature of the medium. The band strength between particles is strongest in solid materials and is weakest in gases. Solid would transmit sound faster, while density of a medium also affects the speed of sound. It moves well through dense material like metal or wood. Sound can move well because their molecules are closer together. The elastic properties have greater influence on wave speed. It returns quickly to their original position after disturbance. An example is iron and metal, because they transmit sound well as they are very elastic. Increasing the temperature decreases density inasmuch as the material expands. Sound travels faster at higher temperature. Since the language of physics is mathematics, so let us calculate now the speed and temperature of sound. Now take note that sound travels at about 331 meters per second in dry air at 0 degrees Celsius. Greater than 0 degrees Celsius, the speed of sound increases by about 0.6 per meter per second for every 1 degree Celsius increase in temperature. This is shown in our equation. V is equal to 331 meter per second plus 0.6 meter per second per degree Celsius multiplied by temperature. And for temperature, T is equal to V minus 331 meter per second divided by 0.6 meter per second per degree Celsius, where V is speed and T is temperature. Now, let us calculate the speed of sound in reference to its temperature. In our sample problem number 1, what is the speed of sound at an altitude of 30.5 km where the temperature is about negative 50 degrees Celsius? In the speed of sound, there are only two variables involved. So we have the temperature and the speed. Alright, let us answer. The given is temperature, which is negative 50 degrees Celsius, and we are looking for the speed of sound. The formula that we're going to use is V is equal to 331 meter per second plus 0.6 meter per second per degree Celsius multiplied by its temperature. Solution: V is equal to 331 meter per second plus 0.6 meter per second per degree Celsius multiplied by its temperature as negative 50 degrees Celsius. So, let us multiply first 0.6, positive 0.6 multiplied by negative 50 will give us a negative answer of negative 30 meter per second. So, let us add this to 331 meter per second will give us the speed of sound as 301 meter per second. Alright, number 2. What is the temperature if the speed of sound in air is equal to 1,228 meter per second? The given velocity is 1,228 meter per second. And we are looking for the temperature of sound. The formula that we're going to use is temperature is equal to V minus 331 meter per second divided by 0.6 meter per second per degrees Celsius. So our solution, T is equal to the value of V, which is 1,228 meter per second, minus 331 meter per second divided by 0.6 meter per second per degrees Celsius. So, temperature is 897 meter per second divided by 0.6 meter per second per degrees Celsius. Again, let us cancel meter per second and meter per second. So, the answer is temperature is 1,495 degrees Celsius. Temperature and the velocity or speed of sound is computed. For the application of sound, geologists were able to model the earth by means of waves passing through it and use these sound waves to locate rocks that may contain oil and natural gas. Moving on to the properties of sound. So the properties of sounds are reflection of sound and refraction of sound. The reflection of sound described as the turning back of wave as it hits a barrier. And echo is an example of reflected sound. The multiple reflection of or echoes in a certain place is called reverberation. It often occurs in a small room with height, width, and length. Dimensions are approximately 17 meters or less. In theaters and movie houses, there are reverberations and echoes, but not pleasing to the ear during a play or movie. So, to lessen this, they use curtains and cloth cover for the chairs and carpets.
In the field of medicine, reflection of sound is applied through the use of ultrasound.
This echo sounding is used by scientists to map the seafloor and to determine the depth of the ocean or the sea. This is just the same as how bats use sound to detect distances. The other properties of sound is refraction. This is described as the change in speed of sound when it encounters a medium of different density. This change in the speed of sound during refraction is also manifested as sort of bending of sound waves. Sound travels faster in hotter media. It heard better in far areas during nighttime than during daytime. When sound propagates in air, where the temperature changes with altitude, sounds bend toward the hotter region. In this case, refractions happens. The refraction is due to the different refractive indices of the air because of the difference in temperature. Sound waves bend or refract when they travel through air on uneven temperatures. Sound waves moving through air during the day are refracted upward because of the warmer air near the ground. At night, sound waves are refracted downward because of the colder air near the ground. This is manifested in our illustration. Other applications of reflection and refraction of sound in our daily life. So refraction happens underwater due to varying water temperature. This can be problematic for vessels trying to chart sea bottoms featured by bouncing ultrasonic waves off the ground. But it could be useful for submarines that don't want to be detected. Ultrasound procedure in medical diagnosis. The ultrasonic waves strongly reflected from outside of organs, so can give a picture of the organ. Sample, if object is moving, example, the baby's heart, then the reflected wave is Doppler shifted. This is measuring the shift can give baby's heartbeat even when fetus is just 10 weeks old. Also, dolphins and bats use ultrasound reflection or refraction and Doppler effects to get a sense of their surroundings. That is for today. Thank you for listening. Keep safe, everyone, and God bless.